we're going to introduce enclosed stacked rapid sand filters briefly, talk about some of the advantages and challenges of working with stars as a filtration method. So I want to begin with this insight about what is different between when you finish backwash of a stars filter compared with a standard rapid sand filter. With a standard rapid sand filter, when you backwash, you are always pushing water up through the sand. And so there is water above the sand that just was used to backwash the filter. And so if you haven't run water for a very long time during backwash, there is still a higher concentration of turbidity or particles in the water above the filter when you finish backwash. And then when you start filtering with a conventional rapid sand filter, you start putting water in the top of the filter, and that water goes down through the sand. And so that means that the first water through the sand in a conventional rapid sand filter is the water that was just used to backwash the filter, which is slightly dirty. And that is one of the reasons why the first water that comes out of a rapid sand filter is a poorer quality, in addition to the fact that the filter is still in the ripening stage. Okay, so let's look at what happens in a stars filter. In a stars filter, here's the stars filter like in backwash mode. And when we open up this valve up here and stop the backwash exiting through that siphon tube, then water continues coming in through this inlet box. And the question is, where does that water go? Well, the water that's coming in the inlet box wants to, or the only option for it to leave is to get to this outlet box, because the outlet through the backwash siphon has been blocked. So the only outlet is through the outlet box, but that outlet box is quite high. And so the only way the water can get into that outlet box is first it has to increase the water level above the filter. And so once you get to filtration mode, it looks like this. The water level has come up in the filter box. And so the water that is now above the filter in that filter box is a mixture of water that was there right at the end of backwash and water that got injected somehow as that box was filling. So the question is, where does the water come from that fills the filter box at the end of backwash? So how does the water get into the filter box? How does the water get from this inlet box over to the filter box? And the answer is, it goes through these 4 inlet pipes. Some of it goes in at the top, some of it goes in lower, some of it goes lower, some of it goes all the way at the bottom. But if you're water and you're lazy and you try to find the easiest path, where do you most likely enter? The shortest path is to avoid the sand. So the easy path is to go in this very top inlet, go into the very top of the sand bed, and then go up into the filter box. That makes sense? So that's how the water gets into the inlet, into the filter box at the end of backwash. So does that water is slightly dirtier because it includes water that went through the filter during backwash. So does that water ever go through the filter? It's interesting. The answer is no, it never goes through the filter, because the next thing that's going to happen is you're going to switch over to backwash mode. And when you switch over to backwash mode, you flush all of that water through this siphon pipe, and it goes to waste or to your backwash recycle tank. So the water that's above the filter in the stars filter never gets filtered. It gets dumped. So it's both a good thing and a bad thing. It's good that because that's dirtier water. It's good that we're not filtering that because it's dirtier water. It's bad in that we end up dumping a fair amount of water to make this transition between filtration mode and backwash mode. One more advantage, there is no danger of running out of water, out of filtered water to backwash the filter. So in a conventional system, you backwash the filter with a rapid sand filter, you backwash with water that you filtered and you put in a clear well tank. And then you take that water from that tank and you pump it back up through the filter. And if that clear well tank is empty, you're stuck. You cannot backwash your filter because you don't have water to do it with. And that is actually a failure mode for a conventional water treatment plant. This can't happen with a STARS filter because we don't use filtered water, we use clarified water. So that means that as long as there is water coming into the plant and going through your flocculator and your clarifier, you've got a source of water to backwash. Of course, with the caveat that there must be enough water coming in to fluidize at least one filter sand bed. And now I want to talk about enclosed rapid sand filters, enclosed stacked rapid sand filters, and open stacked rapid sand filters. So enclosed versus open. There's 3 enclosed stacked rapid sand filters that were built for a village in India, in Jharkhand, India. And there's the big box, a big filter box for a open stacked rapid sand filter. In your assignment that you're working on, I forget what the minimum flow rate is that you came up with for your filter, but it's somewhere on the order of 10 liters per second. That if you're trying to design a filter that's less than 10 liters per second, it ends up being too small for a human to comfortably work inside and build this tank. So that sets a minimum flow rate that we can use for open stacked rapid sand filters. And then below that, we have to switch to enclosed built inside a pipe systems. And they have their own advantages. They don't require as much excavation. They don't need to be so tall. An open stacked rapid sand filter ends up being close to 5 meters tall by the time it's all, or 5 meters deep. It's this really deep tank. The enclosed filter doesn't have to be so deep. So here's, see if we can figure out why. So here's 3 views of the filter, both looking at it from 2 different angles and also a section cut. So there's a tall inlet tank, there's a shorter outlet tank, there's this lovely filter canister, which I think in this case is probably like a 2-foot diameter pipe. There's no longer an air release valve that is used to trigger backwash. Here we just use a standard valve, and that's partly because these are now much smaller valves and they're not so expensive, and so it's not worth going to the air lock system. They have the same system of 4 inlets and 3 outlets, which you can see in this middle view, and you can see water going into the filter and out of the filter. And it was a bit of a challenge to figure out how to get all those pipes to line up. Working in the round is more complicated than working in rectangles to figure out how to get everything lined up. But that's at least version 1 of our design. Of course, there's sand inside this filter, and notice that the sand bed is a much bigger fraction of the total height of this filter, because there's something very different about it. So what happens in backwash? So let's think about what's happening over here in this filter, and let's assume that this valve is open and backwash is happening. which means that water is coming from this inlet tank. All of it is going down through this bottom pipe, going up through the filter and out. So what happens if we close that valve? Can anybody see what's going to happen? If I close this valve, and this pipe might be 3 inches in diameter. And so if I close this valve, what happens to the water in this pipe? Maybe it's just so obvious. That water runs out and the pipe fills with air up to the valve. So then what happens when we try to start the next backwash? So the next time you want to start backwash, we open up this valve and now it's atmospheric pressure way up here at the valve, and the height of water in the inlet tank is right here, which means that there's hardly any difference in potential energy available to push the water through the sand bed and fluidize it. So here's the insight. We were counting on atmospheric pressure being way down here so that there's enough of an elevation difference or potential energy difference between the inlet tank up here and where the backwash outlet is down here. So there's enough head or potential energy or elevation difference available to fluidize the sand bed. So if this air fills this pipe, we can't backwash. It fails. We cannot get backwash to start. So there's 2 potential solutions. You could try moving this valve to the very end of the pipe, but it's still vulnerable because when that valve is open, it's still possible for air to sneak up the pipe past that valve and empty the pipe of water. So the elegant solution is to add a water seal at the end of the pipe that prevents air from ever getting into the pipe. So here it is. It's a very simple thing. I'm proposing maybe a 6-inch PVC cap with a little pipe stub in it. Or it could be a bucket, a small bucket. And the water from backwash enters that bucket and then it overflows the bucket. But the bucket always remains full of water. And that means that when you close the valve, there's no way for air to get up into that backwash pipe. And that means that the pressure at the end of this pipe, it's atmospheric right at the overflow of that bucket of the water seal. And that means that we have the pressure difference that we need, or the head that we need, between the inlet tank and the backwash outlet. There's enough energy there to drive fluidizing the bed. So that water seal ends up being a critical piece of the design. If you don't have it, the system fails. Anybody want to ask a question about that water seal? We're making sure that there is no way that that siphon pipe can fill up with air, so that there's always this hanging column of water there, because we need that dense water to lower the pressure inside the top of the filter. Okay, so let's look at the pressure inside the top of the filter. Here we go. So this is a view at the end of filtration. At the end of filtration, the water level in the inlet tank might be way up here. Okay, and that water is coming from the inlet tank. It's going down through all of the pipes and into the filter. And let's follow this bottom one. So way down here, let's put a manometer in and see how far the water rises. So we look, and the water rises in that manometer almost up to the same level as where the water would be in the inlet tank. The only difference being maybe there's a tiny bit of head loss in this inlet pipe. And so that would result in there being a slightly lower pressure at the bottom of the filter than if there weren't any head loss. And at the top of the filter, same thing. It should have been exactly the same water level. Manometer gives the same reading at the bottom and at the top of the filter. Okay, the pressure at the bottom of the filter and at the top of the filter, as measured by a manometer, are the same. And of course, there's sand in that filter. Now, what happens if I drill a hole in the top of the filter during filtration? So let's do that. Let's drill a hole. So I just put a hole in the top of the filter. Maybe the hole wasn't very clear, but there it is. There's a hole in the top of the filter. And I want to know, is air going to come out of the filter? Or sorry, is water going to come out, or is air going to go in? Some of you who said water comes out are exactly right. And the way you can know that is because these two lines that look, this top manometer is essentially connected to this fluid that's in the top of the filter. And the pressure there is represented by the water height in this manometer. And that water height is well above the top of the filter. And that means water will come out. Or put another way, if I had installed a manometer in the very top of the filter, it would have also come up to this top blue line. So water would leak out, okay?